Good morning, students. Today we discuss about Unit 2 Ardens theorem concepts. So, the theory of computation Unit 2 is a regular expression, finite automata language or finite regular languages. In this concept, we study about how the regular expressions are identified from the given deterministic finite automata. The conversion is nothing but automata to regular expression conversions with the help of Ardens theorem. So this is the theorem statements. This is our theorem statements. Ardens theorem is the concept of let P and Q are two regular expressions over the input set sigma. So we consider two regular expressions P and Q, and P which is not contains epsilon values. So P which is not contain epsilon rho. That means the given regular expression which the given automata is compulsory for deterministic finite automata alone. And the regular expression R is to be considered, which is in the form of R is equal to Q plus PR means, which has a unique solution R equal to QP star. It has a unique solution R equal to QP star is our answer. So this is the Ardens theorem statements. So from this rule only we can calculate what is the regular expression is present in the given automata. In unit 1, we studied about the regular expression is given. From the regular expression, we design the deterministic finite automata or non-deterministic finite automata or non-deterministic finite automata with epsilon transitions. Whatever the conversions, everything studied in the unit 1. In unit 2, we discuss about the reverse process. The automata is given. From the automata, what is the regular expression is present in the automata that will be identified or determined. That is the concept we are implementing Ardens theorem. Just we explain the first before going to that, the corresponding R equal to QP star which has a unique solution, the corresponding unique solution derivation will be discussed now. Let's consider P and proof. Let's consider P and Q are two regular expressions over the input set sigma, which is given in the Ardens theorem statement itself. That will be taken up. And consider if does not contain, if P does not contain epsilon, means there exists R in the form of R equal to QP star, which is equation number 1. Now we replace R by QP star in the given equation. So what is the value? R equal to Q plus PR. In the position of P, we replace it by QP star. So automatically right hand side value Q plus PR is changed to Q plus QP star P. Now in this particular equation, the common term taken as outside, the Q open bracket epsilon plus P star P. We already know that the identity rule epsilon plus P star P means the answer will be P star is the identity rule. So automatically Q open bracket epsilon P star P is replaced by Q P star. This has the solution. So from the right hand side we have taken out. Similarly, we will take as a left hand side rule to prove that R equal to QP star as a unique solution. We will prove from the left hand side. So what is the left hand side? R equal to Q plus P. So R is the position of Q plus PR. And replace R by Q plus PR. Automatically Q plus PR, what is changes? Q plus PR into P. So now the value will be multiplied Q plus RP into P is changed to QP plus R into P square. Again replace R by Q plus PR. Again the equation will be changed to Q plus QP plus QP squared plus RP power Q. Again, we substitute R equal to Q plus PR, the same equation in the form of RQ plus QP plus QP squared plus QP power 3 plus etc. plus in terms of in general form Q power Pi plus R power I plus 1. So first a set of statements we have the common term as Q, we will take as the outside. So Q into epsilon plus P squared plus etc. up to P power I plus RP power I plus 1. So we know that from the equation 1, we know that R equal to epsilon plus P squared plus PQ plus up to P power I plus R power P power R into P power I plus 1, where I greater than or equal to 1. This is equation number 2. Consider the equation number 2. From a set of states epsilon to P power I we called as P star. So replaced by this Q into epsilon P squared up to P power I we convert as Q P star and remaining input R P power I plus 1. So now up to now we have the string W, that is our final derivation. Finally, we will get it as R equal to Q P star plus R into P power I plus 1. Now we consider about the string W, which has the length of I. So corresponding length will be I. In the above equation, we represented the characters will be I plus 1 character. So compulsory I plus 1 character is not available in the automata. So it will be negligible. Finally, you will get as R equal to QP star is a unique solution. So in this derivation is very, very important. Based on this derivation only, we will design or we will identify the regular expression which is present in the given automata. So this is our derivation steps. Next, we discuss about example problem. A small example problem we discuss. After that, we go for the next one. So now, consider this example 2 power 2.9.10. Find represent the regular language accepted by the DFA. So Q0 is a starting state. Is also represented in terms of double circle. We represent as a final state. So state will be 0, 1. So what is the value of the state? First, we write the state equation. Q0 is equal to how many transitions are there? Self-proof only available along with the 2 inputs. So automatically we represent 2 transitions. So Q0 is equal to from the Q0 state, 0 is the input. Plus from the Q0, Q1 is the input. And the epsilon symbol will be added here because Q0 is the starting state. So that epsilon is also added. So what is the value of Q0 is equal to Q0 open bracket 0 plus 1 plus epsilon. So we will consider as in general form, the Ardens theorem general form, we know that R equal to Q plus PR. Just compare the equation Q0 into the R equal to Q plus PR format. We will get the answer Q0 equal to 0 plus 1 whole power star. This is the theorem statements we are implementing. Just another example. This is somewhat one minute. This is another example. Here, identify the equation which is present in the regular expression. Equation means regular expression given automata. So how many states? 4 states. Q1, 1, 2, 3, 4. Now first write the state equations. In state Q1, we can call Q1 how many incoming edges in the automata. So from the Q3 1 incoming edges, from the Q2 1 incoming edges. So from the Q2 1 input, so we call as Q2 1 plus from Q3 0 input, from Q3 0. Q1 is starting state, we can add epsilon. So Q1 is equal to Q2 1 plus Q3 0 plus epsilon. Similarly for Q2 is equal to Q1 0 alone. Q3 is equal to Q1 1 alone. Q4 is equal to 1 to 4, 3 incoming edges. Q3 1, so 4 incoming edges. Q3 1 plus Q2 0 plus Q4 0 plus 1. From this event, this is our state automata equations. From this automata, where the output will be presented means in the final state. So the corresponding state equation Q1 will be evaluated means we will get the answer of the final output. For that purpose, Q1 having the solution we required Q2 1 plus Q3 0 plus epsilon. This is our state equations we will consider. We solve the Q2 equation, we solve the Q3 value, we will get the final answer. From the Q1, we have the solution of Q2, already we having Q1 0. Just substitute Q2 value into Q1. Similarly, Q3 also having the Q1 1, just replace the corresponding equation values. That time Q1 is equal to Q1 0 1 plus Q1 10 plus epsilon. So take the common term outside. Q1 is equal to Q1 01 plus 10 plus epsilon. So compare with the Ardens theorem general rule, we will get the answer for R equal to 01 plus 10 whole power star is our solution. So that's all about the Ardens theorem derivation and identifying the regular expression in the given automata.